Hi guys, I'm Shreya Senapaty and I study in BITS Pilani Hyderabad campus. This workshop is in is with the Google Developer Students Club, which I am a member of. And I'm in my second year. I'm in EC, but my passion and interest lies in machine learning, deep learning, reinforcement learning. All the works. So that is sort of why I'm taking today's workshop on reinforcement learning with Q learning, which is one of your most basic algorithms for reinforcement learning. Uh, so today, what my plan for this workshop is to cover the theory behind reinforcement learning and Q learning, since it is quite vast topic and quite in-depth topic. We might not be able to go through codes as such, but if you all want, I will give places you can look through for codes and all later on. My idea was once you do get the theory behind learning, it's a lot easier to code. That is how it works for me. And yeah. So that is my motive for the day, and we will start off with the so I don't know if you guys. Okay, there you go. That's the PPT. Right. So the first question that arises, of course, is what is reinforcement learning, right? And I'm gonna start this off by taking you all back to when you were kids. And when you were kids, you didn't really know what was right or wrong, right? And your parents taught you. And the most common way that parents do teach this is that when you do something right, you get something good in return, right? Like, for example, let's say that you don't want to do your homework, like as a kid, right? But that's something you should do. So let's say you do your homework a day, then they give you a treat, and they're like, okay, you continue doing your homework for a week, and we'll give you something else, and so on, and you get into the habit of doing your homework, right? That is what by psychology is called positive reinforcement. And when you do something bad, like you scream at others, you have stuff like you get grounded, you get timeouts back in like the US and stuff. But like more in an Indian scenario, you'd get scolded, you'd get told that it's wrong to do so, and that's what negative reinforcement is, because you don't really want to anger your parents at the end of the day, right? So yeah, that's basically where your reinforcement learning rises from. This is a very hot, popular topic. It's only come up in recent times, and they're still working on algorithms for reinforcement learning, simply because this is probably the closest that would work to a human mind, right? Because the human mind works on experiences and building up on experiences. And reinforcement is something that you learn from a younger age to realize what is good, what is bad, or which direction or which action you should take. And reinforcement learning applies this on a machine level. So what it does is through exploration and through rewards, it tells the machine that this is the path you should take, or this is the action you should take, because you're going to get the most rewards from this action, right? So that's a basic idea of what reinforcement learning as a machine learning technique is. And in a in a sentence, it would basically be enabling the agent or the computer to learn in an environment where it's interacting by trial and error, using the feedback from its own actions and experiences as it keeps exploring, right? And this comes under one of the types of machine learning, because you have supervised machine learning that's task driven, then you have unsupervised machine learning that's data driven, and then you have reinforcement learning, which is learning from mistakes, something which we do as humans, right? So you get feedback for a correct set of actions and reward, or like rewards and punishments, which should be a signal for what is the positive behavior and what is the negative behavior, right? Okay, so now now moving on. Uh, okay. So what are your key features of reinforcement learning, right? The agent or the learner, which in this case it's not you as a user, but it is the computer itself that is running the program. They are not told what action to take. You won't say that, okay, you know what, go here, do this. But it will discover this with the goal of maximizing the reward, right? And this is done in a trial error search method, right? And at the same time, when you are using a trial error method, you have possibilities of delayed rewards. And what do you do in such a case? You look at long-term benefits over short-term gains, right? When you're in a situation of delayed rewards, because at the end of the day, it's trial and error, and you can have a better reward later on by trial and error. So your goal at the end of the day is so that the direct agent interacts with the environment. And I will go on to talk about the elements later to build up on the agent environment relationship, because in reinforcement learning, this is a very big chunk of your code as well. You have to have a very good understanding of your environment, your hyperparameters and these kind of stuff to be able to build algorithms on it, to be able to tweak the algorithms to make them work better. Okay, so yeah. Right. Here are your here are your elements, right? Okay. So what is the environment? For us, the environment is the world we live in, and similarly for the agent or the computer, the environment will be the physical world in which it operates, right? And I'm going to take the example of Pac-Man, right? And let's say you're making the computer play Pac-Man. Like when you're playing Pac-Man, you try to move it on your own. Like you're moving it this side so it doesn't get eaten and it gets maximum. It eats maximum number of those circular dots, right? For I think that's like Pac-Man is one of those nostalgic childhood games for all of us, pretty much. But now, what if you try to make a computer play it, right? This is where reinforcement learning would come into play. Your environment would be the entire blue screen that the agent is interacting with. And here, since the computer is those Pac-Man that's eating it, that would become your agent. Now, what is your state, right? So let's say the Pac-Man is at the starting point. So the Pac-Man state is that starting point. Let's say it moves one in front, one position in front. So its new state is one position to the north, for example, right? So it is just where it is in that current environment. That would be your state. Now, your action would be what direction or what move it takes. Moving north would become its action, and its reward would probably be eating one of those dots. I don't remember what they're called, but one of those dots or food per se. Yeah. Now, in this case, you would also have negative rewards because if you get eaten, then that would be a negative reward, right? And not a positive one. Right, and then you have something called the value, which is your delayed reward that I talked about previously, and you will have a policy or a method that would map the state to the action. Because what are you looking at? You're trying to maximize your reward, right? That is your goal. So you need to be able to create a policy or a method in a way that your states and actions are mapped, so that you carry out the actions that give you maximum rewards by going to those specific states that will get you that maximum reward, right? So that's pretty much like on a game scale how reinforcement learning would work, right? Now, before I like to move on, I'd also like to give you an idea of some examples of reinforcement learning and where it's currently being used, or where you could see like published papers about it and everything. So of course robotics, right? Because robots work in with pre-programmed behavior in structured environments. Their tasks are also tend to be repetitive in nature, right? So they provide efficient ways to build the general purpose robots. Um, yeah, so you can basically avoid collisions. You can, let's say, the robot has to pick something up and not like pick up garbage, for example. So you give it a reward whenever it picks up garbage. So it's a continuous task, and it's getting rewards for it, so it'll keep doing. That's how it will be programmed, right? So that's one example. I don't know if any of you know about something called the Atari games, which is one of the first places you could see reinforcement learning used, and DQN as an algorithm first came out, which is one of the reinforcement learning algorithms. Atari Games is also a sort of it's a set of games that they created where the computer had to play the games, and reinforcement learning helped make sure that the rewards were like reached, right, through rewards that the final goal was reached in the game. Similarly, there is something called Alphago. Go is a Chinese board game, and it is known to be one of the most complex strategy games in the world. So they created an RL based Go agent called AlphaGo that can play with other people. And it learns by experience. It's something a lot of professional Go players use as well. And it has the capability to learn by playing against itself, since like it has this sort of, the more it plays, the better it knows which moves to go through. Very human like tendencies, if you think about it, right? Similarly, even with chess, when you have the computer playing chess against you, similar thing. Another very common use, something which I'm currently looking at as well, is autonomous vehicles in driving. So when you look at autonomous vehicles, there's a lot of things you have to do. Sometimes minimize the time delays, minimize the time it takes to move from one place to another. And in this case, you have a very clear goal, right? And you're maximizing the reward, which would be minimal time, right? So it would be negative of the reward in this scenario because you have to minimize the time. But there are very clear goals: reduce pollution, save space, save distance or fuel, stuff like this, right? Very designated goals, which is why you can use something like reinforcement learning in these kind of scenarios. So that's where you have a lot of examples of reinforcement learning come up. Uh, as you see, they're all things that need very uh, repetitive tasks, and they have very defined goals as well. So, what are the benefits of RL, right? Like you have ML, you have DL, and then you have RL, and what is the benefits of RL over there? So, RL focuses on a problem as a whole. So, when you look at conventional machine learning algorithms or neural networks and stuff, they excel at specific subtasks, right? But RL, on the other hand, it doesn't divide an entire problem into sub-problems, but it works on maximizing the long-term reward for the entire problem as a whole, right? And it is capable of trading off short-term rewards for long-term benefits, which is not something a lot of other machine learning algorithms or conventional ones can do at the moment. You also don't need a separate data collection step. So you have uh, in ML, a lot of data processing, data extraction, all of that kind of stuff. RL doesn't need that. You're collecting data at every single episode you run the training data through because it learns from the agent's experience itself and not a separate collection of a data or data set that is fed to the algorithm, right? At the same time, it works with continuous data. You can have continuous action data that's given to it, and it will work with that. Again, just to put out there, there's a lot of algorithms that doesn't work with certain RL algorithms. It does work with others, right? And the more new ones, of course, work with continuous data. It also works in dynamic and uncertain environments, right? Because they are built to adapt and respond to the changes that is in the interactive environment it's working in. So that's why the learning is very inherently adaptive. So these are like the very major benefits. Of course, there are challenges. There can be delayed rewards. There can be extensive experience required. These are the kind of things that they have been working on by building out on more and more algorithms. We start off with just Q learning, which is a basic algorithm that's taken further up with DQN, DDQN, TD3, SAT, and so on, right? So you keep having changes to it to tackle the challenges of RL itself. So that's about a very brief overview about RL, right? This is a little bit of how it works. You have an agent that will take an action to the environment based off your reward and the state that the agent is in, and it moves to the next reward in the next state accordingly. So that's somewhat of a flow chart of what I had explained in the beginning about the agent environment interaction. Right. So rewards and returns, I will come back to the slide later on to explain what discount factor is. But rewards and returns are, like I said, just okay, if I'm doing something good, I'm getting a good reward. If I'm doing something bad, I'm getting a punishment, which in case would be a negative reward if you think about it, right? Like because it's very mathematical. So you give it positive, negative terms pretty much, right? And yeah. Okay, so exploiting or exploring. This is something that's very important in reinforcement learning because reinforcement learning you build on your experience and you're looking at maximizing rewards. These are your two main things that I've been building up on. So when you explore, you take actions randomly and you build on experience. When you exploit, you try to get the max value out of it, right? But then here's the thing, if I exploit without exploring, what am I exploiting? I'm really not exploiting anything because I have no information for reference to exploit. But at the same time, if I keep exploring, I will never get my maximum rewards or maximum values because I'm not exploiting enough. So you need to strike a balance between the two whenever you're creating your algorithm, which is another hyperparameter that will come into place called epsilon, right? Which we'll again discuss later with the hyperparameters. But the idea that there is exploiting and exploring and you have to balance both is something that's pretty important in RL in general. Yeah. Okay, something called the state transition probability. It's also matrix, as you can see later on. So pretty much, you have a state S1 and you move to a state S2, right? And you need to be able to put it into like, there's a probability of moving from one state to another state. For example, there's a probability that after this workshop, I might decide to go out with my friends, I might decide to go to my room to sleep. So I have two possible states, and I would decide that based on how I feel, right? So there's a probability I might do this, a probability I might do that. So hence you have a state transition. Okay, my bad. That's state transition probability matrix. But yeah, so you have a state transition probability depending on whether I would move from this state to another state. And a matrix is created out of it to be able to choose which probability to go forward with, right? All of this comes in building the environment of the algorithm itself. Right. Uh, okay, and each row that you see here is moving from it's the probability to move from your original or starting state to a successor state, like from P1 to P2 and so on and so forth, like S1 to S2 and so on and so forth. Right. Okay, something called the Markov property, which basically states that your future is independent of the past given the present, right? And that's how it's represented, saying that PST1, as in your next state, is independent of the past, but depends on your present, and your present state depends on the state before that, and so on and so forth, right? Okay. So this is something called the Markov process. I try to make it my own example, hence you can see all the drawing there. But here's the thing. Let's say you're on vacation and you have only three things to do: sleep, eat, and work out. I know that is not very feasible, but regardless. So the thing is, you have so these are your three states in throughout the day: sleep, workout, and eat. And when you're sleeping, you have some probability to go work out once you get up, some probability to go eat once you get up, and some probability to sleep again, right? And your probability to work out will obviously be less. Probability to eat will probably be more because you'll wake up hungry. But I mean, how many of you here are in college and agree with me that you want to keep sleeping as much sleep as you get, right? Sleep is like one of the best things ever. So yeah, so there's those numbers of probabilities to move from that state to another state, or stay in that state itself, to stay in the state of sleeping, right? And that's how you can see I've given states for everything. After you work out, you're tired, so you probably do not want to work out again. But do you want to eat? Yeah, you'll probably be hungry, so there's a higher probability of you to want to go and eat. Now, this is what is a Markov process. It's a random process. It's a random sequence of states that has a that is based off your Markov property, right? And so you're so basically these chances, these probabilities that are given, let's say 0.1, 0.5, so on and so forth, are transition probabilities. Your probabilities to transition from one state to another or stay in the same state itself. Right. So you can choose a lot of different samples from this particular chain that I've given, right? You could go with the most basic: sleep, workout, eat, sleep, which would be cyclic. Or you could sleep, workout, sleep again, then eat. So there's a lot of chains and it's very random and you can choose anything out of it, right? But there's just a higher probability that you choose this over that and so on. So that's what a Markov process is. Now, what is a Markov reward process? So the Markov reward process is based again off rewards, right? This is where I'm going to go back to my reward slide. And remember, I told you I'll explain discount factor to you then, which is what I'm going to do right now. So the thing is, you have two kinds of tasks. Episodic tasks that have an end state. You know they're going to end now. I will work out for an hour and it is going to end after an hour. Or you have continuous tasks that will keep happening. For example, me learning to code or to code in Python is still a continuous task since I haven't really mastered the entirety of it yet, right? So how would you how would you get returns out of a continuous task? How would you give rewards from a continuous task? And this is where your discount factor comes in. It determines how much importance you give to an immediate reward or a future reward. So it helps you avoid the scenario of an infinity when it comes to continuous tasks. So it always has a value between 0 and 1, and an optimal value generally lies between zero point 0.2 to zero point 0.8, right? Now, that is just the function of how to be, where gamma is your discount factor and RT plus 1 is your reward. So this is the first reward, second reward, third reward, and so on and so forth, right? Um, so here's the thing, like if you have a discount factor, say 0 0.8, and you start off with your first award being 100, then because of the discount factor, it will reduce to an 80, then to a 64, and so on. And as you go towards the end, it will become very minimal. So here, your rewards in the beginning are more important, right? Because the decrease will not be very significant later on. Like it will be very significant later on to a point where it's so minimal it does not account to much compared to the beginning rewards that you were getting. So yeah, that is how it would be with 0 0.8. But at the same time, till a certain point, your future rewards will be you will be interested in future rewards until it reduces to the point where it's not very important. But that will take until let's say 15, 16 episodes. Now, if I have a discount factor of 0 0.2, I would just go 100, 20, and then 4, and that's just gonna like get even more minimal. So how much importance am I giving to future rewards? Not so much, right? Because once you have 124, after that it's so minimal that it doesn't really matter compared to the rest of it in the first place. In this case, you're interested in earlier rewards as opposed to in the case with zero point 0.8 discount factor where you're interested in future rewards. This is what your discount factor is telling you. It's telling your algorithm, are we interested in future rewards or are we interested in early rewards? So that your algorithm can run accordingly. Right? So this is again one of your hyperparameters like epsilon. Right. Cool. So now we will come back to the Markov reward process. Right. So in this, these are the elements of the Markov reward process. But what is it, right? When you add a reward to your Markov chain that you created from your Markov process, that's what gives you a Markov reward process. So it values rewards, it values the rewards that are there in the process as opposed to anything else. So this is when you have something like this. So if you see here, there is more, I've added more states, but what's more important is that there are added rewards that are given to each state. So sleep has no reward. I've given Instagram a negative two because you're not really being productive when you're scrolling through Instagram between your classes, right? And we all know the urge in an online class to pick up your phone and scroll through Instagram. So given a negative reward in the scenario. And attending classes are of course given positive rewards since you will get some benefits from productivity out of it. Let's say some class is more important than the others, which as college students we would know considering you have credit systems and each subject has a different number of credits. High number of credits, more reward because it is more important to your final grading system, right? And then again, I've given going out a reward because a lesser reward than classes, but I've given it a reward regardless because you require it for maintaining social balance in your life and as well as getting some fresh air. So I've just tried to relate this a lot to, our real life processes, or real life daily life examples, and see how you would like probably reward yourself that way. Similarly, you would reward the computer or the agent similarly to take some steps that give you what you require and help you get your goal at the end of the day, right? There's still probabilities, but these probabilities will now be based on the reward since the agent will try to maximize its reward, making it a reward process, right? Okay, so here comes in, wait, right. So you then have NDPs or Markov decision processes, which means now what are we doing? Where, as the word itself says, you will be giving more importance to decision making or judgment as opposed to just rewards. So the process also has judgments involved and hence a decision process. Um, so something that comes in into an MVP is policy and value functions, right? And what are these? A policy is a function that defines the probability distribution of an action for each state that you have. So let's say a policy is written by the symbol pi. So let's say your agent at a specific time follows in policy pi, then the probability that the agent is taking that action at that particular state at that time. So let's say it's at state S at time t. At that state S is what is your change in policy, right? So that is mathematically how your policy is defined, and you can see it over here as well, right? That's your action and that's your state. Now, what is the value of a state? The value of the state is when the agent is following a policy pi, it is expected there is expected returns from S by following that specific policy, and that is the value at that state. So that is also called a state value function or just a value function. It gives you the expected returns if you started from that state and you went on to successive states. But what is the successive states? Based on the policy that you have decided, right? The policy function that you have decided. So here's the thing. The policy itself is rigid or like stochastic, but the value of your state is not. That can change depending on the change in policy, right? So that is something you should know as well. So yeah, this is where one of the equations I previously showed, the Bellman equation, comes into place. It's known as the Bellman equation for a value function, right? And since I'm doing value functions, this is why this comes up here. Right, so what do you see here? Here the E is basically max, which is in the second interpretation of the same equation. R is your reward at that state following that action, plus your discount factor and the value of the previous state, right? So the value of the previous state into your discount factor added with your reward at that state and the max value. Now, there's a question here, right? The most obvious question. Why are we using max and why are we using discount factor? Now, your max function helps the robot to choose a state that gives it the maximum value being in that state. And that is what we're looking for. So something you should know is everything we're looking for, we're trying to maximize. We're trying to maximize the reward, we're trying to maximize the value you're in. So hence the max function. Now, why the discount factor? The discount factor tells the robot how far it is from its destination. So this is why you would use a discount factor for the uh, in the algorithm itself, right? So here's the thing, like how does this work? This is like a scenario where I'm I'm Pac-Man and I can move front, I can move to my sides, or I can move back. Let's say I'm not at the starting position, I'm somewhere in the middle. I have four places to move. And what would the way I'd move be based on? I get maximum rewards, I don't get eaten, right? And that is what the policy would decide how I'd move based on which states will give me the maximum value. And the Bellman equation helps you determine where you're getting that maximum value. Right? So it's a equation for your value function. It's a modified equation of the value function. Per se. That is what your Bellman equation is. Right. Okay. Yeah. So what it does in a way is that it would, let's say my north, it would put in, if I move up, then I'd probably get a value of 1. And if I move to your right, I'd get a value. So basically, each each step you're taking has a value. You assign it a value, and you are going to try to take steps in the way that you get when you add them, you get maximum value. Right? That's pretty much it at the end of the day. Gives you what action you should take next. Right. This is where we come in with hyperparameters, which is what you have: learning rate, discount factors, and epsilon. And your main goal is to achieve the optimization of these three parameters. Right now, here's the thing: what are these parameters? Is something I've explained, except learning rate. Here's what learning rate is. Um, you need to learn, you need to train the model to learn, right? So you need to have a rate or a parameter that tells it, okay, this is the rate at which you're learning. Pretty much what the learning rate is the word itself. Why does it come into play, right? So you have the Bellman equation as somewhat of a memory for the system itself, because it stores what the state's values are and hence creates a sort of memory for the system to know, okay, this is how I should move, or that is how I should move, because you have stored states. Now, in that, how does that happen though? That happens through the system itself learning that, okay, this is how it is, and this is how I should be moving and all. Um, one So that's what learning rate is, and that's something I think any of you who've also used ML or neural networks also know the concept of a learning rate, because even neural networks need to learn, and it's a very similar thing. With the only difference that neural networks work on subsets, and this works in the problem as a whole. Your hyperparameters are very important to the functioning of the entire program itself, and they are initialized in your environment in the beginning. Because you have to achieve optimization of these three parameters to be able to get a successful and achieve and be able to be successful and to be able to achieve your goals, right? So, how would you optimize this is what the question comes into play. Uh, Right. So your learning rate as you keep learning would decrease because you gain larger and larger knowledge base. For example, you explore and exploit at the same time, right? And when you explore and exploit and you create a strike a balance between these two using epsilon, you would get more and more knowledge about your environment as a whole. So once you have more knowledge, you have learned more, and hence your learning rate will decay or distort or decrease. Because now I don't need to learn as more. I've learned this much about the environment. Thing is, it's not like the world in the sense that you have an unlimited amount of learning to do. It's a specific environment that you have set up for the agent, for the computer, and so it's pretty limited, right? And hence your learning rate decreases as you move forward. That's how it should be. And your discount factor, on the other hand, would as you get closer and closer and to the final stop that you're looking towards, your preference for your near term reward would increase, because clearly you're not going to stick around long enough with the long term reward. Let's say I have a time limit at 2 hours. The first 1 hour I can obviously look at long term rewards. But now I have only an hour left. I've already used up 50% of my time. I have to look at near time rewards because I will not be sticking around long enough to look at a long time reward, which is when your discount factor looks at nearer time rewards, which, like I explained to you, could be lesser because with the example of zero point 0.2, like I explained to you, it would be 100 plus 20 plus 4, where you're looking at near term rewards. But when you have a higher discount factor, you're looking at longer term rewards because the decrease is the slope of decrease would be lesser as opposed to the slope of decrease with near term rewards and a lesser discount factor, right? Epsilon again, like I've already explained what epsilon is, but how would you optimize it? You would need to explore. So once you develop your strategy, you would need lesser exploitation and more lesser exploration and more exploitation. My bad. So you need to explore in the beginning and exploit more in the end. So you have to adjust your epsilon similarly, right? And now, how do you tune these hyperparameters, right? And the best way to do this is to use a function that would make sure that the parameters you select would result in a best reward by time steps ratio, because you need higher rewards in lesser time steps. Hence, this ratio should be higher. So best ratio for this, because you want to choose parameters that give you maximum reward, and it should be as fast. There's no point in me waiting for 2 hours to get a reward of 100 if I can get a reward of 150 within 1.5 hours, right? So lesser time, more rewards. That's what we're looking at. Hence, the reward to time step ratio should be higher, and the parameters have to be tuned up in the same way, right? So something that you can, my bad, a fancy way to get this right, like a particular algorithm that helps get you the values right, is called genetic algorithms. You can search that up later on if you do want to. So that's how you tune your hyperparameters while building your environment. Because everything I've explained till now is all about building the environment that you're working in. You have to build the policy, you have to build all this kind of stuff. And then you move on to what algorithm should I use? Should I use Q learning? Should I use DQN and so on and so forth? we're going to just talk about Q learning because it is one of the most basic uh, strategies, and it uses something called the greedy epsilon strategy, right? So what it does is your epsilon rates are higher in the beginning so that the agent can explore the environment and randomly choose actions. This is because as like a newbie to that environment, it does not know what is happening in the environment. And then your epsilon rate decreases and your agent starts to exploit the environment. Now, during this entire process, it becomes more confident in estimating something called Q value. Now, this will come into place in Q learning, what Q values itself are. But yeah, that is basically what the greedy epsilon strategy is, and it's a basic strategy that's used in pretty much every algorithm that's out there at this point. Um, yeah. Okay, so something very important in Q learning is the Q function because the Q function is what drives Q learning in the first place, right? So you have Q values for particular states. So they're given, so this each state is given this particular Q value, right? And you have an expected discount and cumulative reward that's shown in your green colored box. And that is at a given state in action, as given in the purple box. The E here again stands for maximum value. You try to take out the maximum value like we saw with value function. And that is pretty much how the Q function works with a particular policy pie that will that you will have made already. So that is what your Q function is. How does Q learning work, right? This is the part of the algorithm that comes into play. Right. So here's how Q learning works. The first thing you do in Q learning is you create or initialize a table. So of course, the first thing you do is create an environment, like I've already told you, and then you initialize or create a Q table. Now, what is a Q table, right? Your Q table stores all your Q values. It stores whether I move this way, what value it will get me, and it it stores all of these values in the table itself. So it's a matrix that follows the state action. It's the shape of the state and action, and you start off by initializing everything to zero, and then you update and store Q values after every episode. So it's somewhat of a reference or a memory table to select the best action based on these values that you've entered into this matrix, right? Just give me a second. Right. So that's the first thing you do. Then, of course, your next thing is to make the updates by taking the action, right? And that is where, again, your explore and exploit comes into place. You decide to interact with the environment by doing either one of them. More exploring in the beginning, as I said, and more exploiting towards the end. Now, that's after this, you update the Q table. And the updates occur after each step or action with Q learning. As you have more, as the algorithms advance, you see that updations will occur after a set of actions. This would reduce the amount of time because you don't have to keep updating after every step, right? You'd keep updating after a certain number of episodes, like a decided number of episodes. Um, yeah. So how does it work? The agent starts in, let's say, state one, takes some action and gets a reward one. Then it selects an action by referencing the Q table that has the highest max value, or it can do this on random like it would do in the beginning. Since in the beginning all your values are zero, right? So that would be decided by epsilon. And then it would update the Q value, right? So here is how your updated function would look as you keep choosing. So it would be based off alpha and gamma, your discount rate and your learning rate. So the learning rate pretty much just tells you, do I accept the new value versus the old value? Because you're learning, right? When you get taught something at school, and I remember this happened a lot with me in particular in math. The kind of teaching that you have in like Indian schools is very rote based in a way, right? And I'd go back home, and my mom, who is a math teacher, she would teach me a very logical way to approach the same thing. So it would be my choice whether to learn and take what my mom's taught me along with what my teachers taught me, or not accept the new thing that my mom's taught me, or the new method that my mom taught me, and stick to the old method that my teacher taught. So that's some kind of dilemma that you've all been at some point of time in your life. I just took academics because we're talking about learning. Uh, but yeah, that's pretty much what your learning rate does. And the learning rate is taking the difference between the new value and the old value, and then you multiply that value by a learning rate. So this gets added to your previous Q value because it tells you, okay, how much have I learned? How much have I moved towards the direction of the next better possibility, right? And then you have the gamma value, again, already explained. But yeah, it just tells you how much am I balancing between immediate or future reward, and updates the same thing. Then you have the reward, and then you have the max, which tells you takes the maximum of the future reward and applies it to the reward for the current state, right? So this is what Q learning does. You are basically allocating future rewards to current actions. And why are you doing this? To help the agent select the highest return action at any given state that it is at. So that's pretty much what you're doing with Q learning in general. You initialize the Q table, you choose an action, you perform the action, you measure the reward, and then you update or evaluate the reward accordingly. That's pretty much an overall background of how you would code Q learning. So very it's not a very big deal to be able to code it once you realize what parameters you're optimizing and looking at. Right. So I that's pretty much how Q learning works. Code-wise, there's a lot of codes on OpenAI and DeepMind Labs and all these kind of places that you can look at. You can look at stuff online as well. Um, but at the end of the day, you're just creating an environment and you're initializing your Q tables, uh, initializing it with zero, by the way. Then you start exploring, travel to the next state as a result of the action that you've taken. For all possible actions, you select the one with the highest Q values and update the Q values as you move on. And then when you reach a goal state, you keep repeating the process to be able to create a sort of memory for the computer itself, for the agent, which is the computer. Yeah, so I think I pretty much covered most of what I wanted to talk about. Um, when it comes to the coding part of it, I haven't actually put up any code on the presentation itself, but yeah, just look up codes, and because the codes, again, explaining the codes would take me a lot longer than what the given stipulated time of the workshop is, which would bore you all out. But I hope this was pretty comprehensive and like pretty short and comprehensive for you all to understand and be able to try coding all of this on your own. Are there any questions or answers? You can do like a question answer session and then probably end this. Mm, I don't know if I can see anything on the chat itself. Okay, anyone has any questions that they want to go ahead and ask, now would probably be the time to do so. All right, I don't really see any questions. Thank you, Riddhi. Thanks a lot. So yeah, that was pretty much it. If you want any resources, textbook-wise, I have used Reinforcement Learning by Richard Sutton, which is pretty good. There's a lot of online platforms, like I said, OpenMind AI, that has its own like AI gym and everything, where you can learn reinforcement learning as well. So yeah, feel free to go and explore and try writing your code, and I hope this helps. PM me if you have any questions this year from the college. You probably do have my number or Facebook ID. So, yep, that's the end of the show, and I hope it was very clear and understanding, comprehensive to all of you. Thank you so much for being here and listening to me speak.